problems with understanding V1 by efficient coding. We have shown that if we assume the reciprocal field transforms are linear, and if we approximate the input signals and noise as Gaussian, and that the coding efficiency is done by maximizing extracted information while minimizing the output cost with this objective function, then the coding transform K can be analytically understood to have these three conceptual components. And if we apply this to V1, we see that although individual V1 reciprocal fields could be seen as arising from a particular one-time complete representation from this framework, the whole V1 representation is overcomplete. This is very puzzling since V1 has about 100 times as many neurons as retina does, so that many different preferred orientations can be covered by different V1 neurons, and spatial frequency tuning curves can overlap extensively, and there are many reciprocal fields covering any visual location. So this overcomplete representation makes the representation very redundant, and this is contrary to what coding efficiency means, and more neurons requires a higher cost. This puzzle is not resolved if we remove this assumption that the signal and noise need to be Gaussian, for example, by doing numerical simulations for the efficient transform rather than using an analytical solution. And it's also not resolved if we modify this objective function somewhat, for example, by using another objective function of sparse coding in a similar spirit. Let's have a closer look at this Gaussian approximation. How good is this approximation? So first of all, when we have a zero mean Gaussian signal S, it has such a probability distribution. It means that the correlation between different signal components, for example, Si, Sj, etc., can be characterized by the first and second order correlation between the components, and that higher order statistics or higher order cumulants are zero. In particular, all the higher order moments of the signals can be completely determined by the first and second order correlations. For example, for a single scalar S, if it's a zero mean Gaussian, then this should be its kurtosis and has a value of 3. So therefore, for any signal S, the deviation of the kurtosis value from this value 3 can be a measure of how non-Gaussian this signal is. For another example, look at two signals S1 and S2, and when they are having zero mean and they are Gaussian and they are uncorrelated, then this quantity should be equal to 1. Now let's look at an example visual image. Like this one, it should contain both the low and higher order statistics in this original image S. And we can apply a whitening to it so that it should remove the first and second order correlations in an image, and this is the outcome. O, all the pixel values O, and if there's no higher order statistics in the natural images, then all the pixel values O in this output should be uncorrelated Gaussian signals. Here is the joint probability distribution of two neighboring pixels O1 and O2 from this output image, and this axis represents the value of O1 and this for the value of O2, and the brightness of each location represent the probability of O1 and O2 take these respective values. And from this, it is apparent that these two pixels, the two neighboring pixels, are not correlated up to the second order. If we look at these individual pixels, this is the probability distribution. So the horizontal axis are the pixel values, and the vertical axis is the probability density. And we use log of the probability density in order to be able to see these very small probability density values more easily. Here we did the same thing, log probability, yeah. But anyway, in blue, we plot the probability density coming from this whitened natural scene pixel values. And in red would be the case if they were Gaussian signals. So this red curve and the blue curve, two probability, they share the same mean and the same variance. However, the blue curve seem to have longer tails and more sharply peaked. And this is reflected in higher kurtosis of this blue curve than if they were Gaussian for this pink curve, it should be equal to 3. So obviously in natural images, the statistics are not Gaussian. Now let's also look at the higher order correlations between O1 and O2 by plotting a conditional probability. Yeah, and so this is each column is for a given O1 value, and each column plots the conditional probability of O2 given an O1 value. And you see when O1 is here, so which is kind of near 0, this is positive O1, negative O1. When O1 is near 0, O2 is also mostly near 0. Yeah. However, when O1 is bigger, positive, then O2 is much more spread out. Similarly, when O1 is more negative, O2 is also more spread out. Yeah. And so therefore, O2 is somehow dependent on O1 when it's visualized this way. Yeah. And so higher absolute value of O1 is going to more likely making O2 also having higher absolute value compared to near 0 O1 values. Yeah. And so therefore, we can even calculate to quantify this quantity to characterize these kind of correlations, and that's equal to 5.1. If O1 and O2 are uncorrelated Gaussians, they should be equal to roughly about 1. Yeah, this value, but this is 5.1. So another signature that these pixel values after whitening of original image, they are not Gaussian distributed. We may wish to remove the higher order redundancies to make the code even more efficient. Yeah. So that in addition to whitening, which is what Retina does in noise-free situations, one adds additional linear or nonlinear transform to achieve this. If we just do an additional linear transform, and then this is equivalent to a direct linear transform, okay, and this can be approximated by having a rotation matrix U on top of this whitening matrix K whitening. This is because, as we will see next, in natural visual images, the lower order statistics dominates. So therefore, if we want to remove higher order redundancies, this should not undo the second order decorrelation that's already achieved by this whitening. And we have shown in previous video clips that having a multi-scale coding in V1 in a one-time complete but not over-complete representation is like such a transform. However, this kind of transform will not give us an over-complete representation in V1, and nor is it clear whether or how much this kind of transform removes higher order redundancy. For nonlinear transforms, activity normalization models have been tried, and it does help to reduce such kind of higher order correlations. However, again, for coding efficiency, it should not adopt an over-complete representation in order to maintain the second order decorrelation. Now, before we strive to remove all these higher order redundancy, we can also have a calculation to see how much is this redundancy in this higher order. Now we see that this whitened image should no longer have lower order redundancy, so let's calculate. Yeah, so we can first of all calculate the entropy of each individual pixels. Okay, after we have already discretized these pixel values into 64 equal size bins, and you can find that one pixel entropy is about 3.4 bits. Okay, so now let's look at the joint entropy of two neighboring pixels. If they're completely correlated, they should be about the same as twice that. And so now this is 6.64 bits. So if they're really twice that, we can calculate the redundancy, and this redundancy really is less than 3%. So it's actually a small percentage. This redundancy includes only the higher order redundancies, because by then the lower order has already removed. But let's look at the lower orders. In the original image, we can do exactly the same thing, but take this pixel value S before the whitening, and we find that for exactly the same grayscaling discrete values of 64, you have, this is the single pixel entropy and neighboring two double thick pixel entropies. And look at this, this is not the twice of that. So additional pixel does not add much more entropy, so because there's lots of redundancy, yeah, so the joint entropy is not much higher, and the redundancy is almost 50%. And so therefore, from this one can conclude the higher order redundancy is relatively negligible compared to the lower order redundancies, which we more or less removed by whitening. It's hard to imagine that the brain would want to build a huge V1 just to remove this small residual amount of redundancy. And this also shows that although visual inputs are obviously not Gaussian, but if one measures the input statistics by entropy, then the Gaussian approximation of visual inputs is not a bad approximation. We can notice that this image has all the essential information about the visual objects in the original image. Meanwhile, we can make another image. This is made by Fourier transforming the original image and then randomizing all the phases in these Fourier waves and do the inverse Fourier transform. And just by doing that, all the essential information about these objects are gone. Now, however, because this image has the same Fourier amplitudes as the original image, then all the first or second order correlations between pixels are the same as this. And from this, we see that the essential information about visual objects are contained in the higher order redundancies, but not in the lower order redundancies. So therefore, perhaps it's a good idea to keep these higher order redundancies rather than removing them, even though this keeping them is for the purpose of object recognition rather than for efficient coding. Now let's summarize some of the main problems with understanding V1 solely based on efficient coding arguments. First of all, there's no apparent bottleneck after the optic nerve. And secondly, there is no quantitative demonstration that V1 significantly improves coding efficiency over the retina. Now, if the code can be made more efficient after retina, why not doing it right away in the retina rather than waiting till V1, other than trying to combine inputs from the two eyes? With such an overcomplete representation in V1, and with a limited nonlinearity in V1, it is highly unlikely that V1 neural responses are more decorrelated than the responses in the retina. And there is yet no reliable quantitative measures to show whether and how overcompleteness can improve efficiency, reduce power consumption, or to get more independent components. And V1 responses are very much influenced by contextual inputs outside their classical resistive fields, and the current normalization models and simple coding efficiency considerations are not sufficiently adequate to address them. Thinking beyond efficient coding, here are some of the possible leads. One is to build a representation for object invariance. And also another is efficient coding really concerns the information, the amount of information. But perhaps it's time to think about the meaning of information and about attentional selection for a small fraction of information for deeper processing.